the title of our presentation, or some keywords. We will focus on actual pollutants, eternal pollutants, named PFAS, and particularly PFAS pollution in soil, and how to manage those compounds in soil, to extract those pollutants before analysis. And we will explain all in detail this morning. And don't hesitate to send some question to us during the presentation or after, if you like. This is the first online conference of our project. It's a big change for us to start this series of conference. In our side, we have we're thinking about a second step, maybe in next April, to do a training session in Angers. So we will communicate about that later. But today we can start, if you like, Diogo. We can start now. What do you think? It's okay for you?
Yes, I think we can start.
Okay. So this online conference will be partitioned in three. The first part is my presentation. I will give you an overview of the E-SPFdigit project, and introduce our contribution in the University of Angers. After that, Malak will focus on the presence of PFAS in soil. She will explain all about PFAS and how to extract those compounds and to conduct those extraction to analytical techniques. The part 3 will be focused on sensor technology, particularly electrochemical sensors technology we developed, dedicated to PFAS monitoring and analysis by Adil, AIT-YAZZA. And it's for me a real pleasure to work with them. And they are very dynamic, and we are also really happy to participate with all our colleagues in the E-SPFdigit program. We are 9 European countries, including France, and the main of our work together, the 18 partners, is to develop a digital tool for real-time monitoring of chemical like PFAS, but also pesticide, heavy metals, nutrients, and also microbiological organisms like fungi in soil and crops. We have a big chance to work on pilot sites in Greece, in Bolos, and in Spain, in Murcia. The kickoff meeting was organized in Thessaloniki by CERT in October 2024. And the second one in Wageningen, the beginning of last November. In France, we are two partners in the east with the Crete and Estelle Marin and her team, and us in the east in Angers University. So for a global overview of E-SPFdigit objectives, we can detail 6 objectives that you can read with me, but I can explain that our main aim is to develop systemic analysis for improving sustainability, food resilience, and safety use of soils in presence of pollutants. We work on the development of portable solution, handled, easy to use on site, and treat by AA the data. we also develop robotization of the different tools we will develop and put on a drone. The idea is at the moment to focalize on the Nexus soil plant because we have a big constraint and a big ambition. This big ambition is to better manage the pollution presence in soil and the barrier with tomatoes to grapes and also potatoes. So we are really focusing on foods, human foods. And the last objective is to work on open science and innovation under a multi-actor approach. Now we could more focalize on our work in the University of Angers. The first year we focalize on the classical extraction process, which is done in 7 steps. As you can see, this is a classical extraction protocol from a down spike soil with PFAS, for example. We do agitation, sonication, centrifugation, concentration with solid phase, filtration, and at the end put sample extracts in the chromatography technique. Malak will explain in detail this tool. But all this chain is used in lab. Okay, but our work will be to miniaturize this chain, and we have started to do that. The miniaturization we actually permit to decrease the 7 step in 4 steps and from 90 minutes to 30 minutes for one analysis. And this morning we will focalize on the extraction elution steps by filtration and cartridge extraction, and couple with electrochemical sensors dedicated to PFOA. It's one of the PFAS, which is a sort of reference of PFAS compounds. And at the end, we hope to prepare one cell that we'll put on the drone hopper to conduct diagnosis of soil in the E-SPFdigit project. So I was the first. Now Malak will continue, and Adil will finish the presentation. So Malak, it's your time.
Okay. Hello, everyone. Thanks, Maxime, for the introduction. And I'm glad to see you all here for our first conference about PFAS. So I will share my presentation. As Maxime said, so today I'm going to present all about the PFAS, especially in soils, from the extraction to the analytical techniques, especially the lab techniques like the LCM SMS. So the aim of my presentation will be focalized on different parts. We have I will introduce PFAS. What are these PFAS? Then how do they spread to the environment, their impact on health, human health, the current regulations, and after that, the analytical process for the PFAS analysis. So I will start with the introduction. So PFAS acronymed with they are acronymed with PFAS, but they are the per and polyfluoroalkyl substances. We need to know that they are synthetic chemical compounds. They are not naturally found in the environment. So they are based on a chain of carbon and fluorine and fluor. So why we say per and poly? So per, when all that change, the chain of carbon is all linked to fluor, and poly when this chain is not totally linked to 100% fluor. We have different type of PFAS. We have the long chain PFAS and the short chain PFAS. So we say long when the chain is bigger than, like the number of carbon is bigger than 8, and short when the number of carbon is smaller than 8. On the market for now, we have more than 40,000 molecules of PFAS, and there's some because the definitions are now evoluting. This number is also increasing depending on how we define these PFAS. Because of the link between the carbon and the fluor is their electronegativity is difference of electronegativity is really high. So these chemicals or these products are this link is very hard to be break. So it's released as a very slow decomposition. And so they got the name of forever chemicals because we cannot easily break this link between carbon and fluor. They have different properties. They are non-stick, waterproof, and heat resistant. So because of their resistance to the water, because of the resistance to the heat, to the water, to the oil, they are being really useful in our in our life. And since 1950, they have been widely used in various industrial fields and also in our daily life. So if you want to go like on to see how this PFAS has evolved in the dates. So it started in 1938 when some researchers in the United States were like working on refrigerator systems, and they found accidentally the molecule of PFAS, and the first molecule of PFAS was called Teflon. It's called now, the commercial name is Teflon, but its name is PTFE, the polyethylene fluoride. In this time, this type of molecule was not really used. Their properties didn't like take the attention of the researcher, but then because this molecule has been resistant to a really high temperature, it has been used in the Manhattan Project for the development of the atomic bomb, where they wanted to have like a solvent that can resist to high temperature to do the uranium enrichissement. So this in the 1940, it was the first time PTFE, or the first molecule of PFAS, Teflon, was used. After that, in the 1949, the PTFE was released to everyone, like to the commercial side, and it has been used for everything, like in the industry as for the high scale commercials. After that, in the 1950, it was the first time when Teflon was used in our in our kitchen products, like the all of the non-stick pan. After that, in the 1960s, also there has been the development of the new PFAS, new type of PFAS. It's aqueous film forming foam. It's used in the extenter products to reduce to eliminate the fire. And since that, the PFAS has been used widely in the industry. In the years of 2000, like recently, we can say PFAS has been widespread in all over the world. And the thing is, during this time that in 2001, the company that has been that discovered this Teflon product has been accused to contaminate more than 70K person in PFA, which is one of the molecules that we can find in the family of PFAS. And today, we see that we have an increase in the supervision of for the PFAS, but at the same time, we have the development of a new PFAS for the economic and the commercial part. So since the year of 2000, the studies have been conducted more and more to see the consequence of PFAS on the human health. And the International Agency for Research on Cancer has classified the PFA, which I introduced some minutes ago, that it's considered as one of the PFAS that are can be carcinogen. So here is a bit of the history of PFAS. How did it start and now? It's been important to know how do this PFAS can be spread and distributed in the environment. So the distribution of PFAS was started as the main major source for this distribution come from the production process for these molecules, or all the industries that produce these molecules. At the same time, also we have the industry or the manufacturers that use produce product that use PFAS. So these also can contribute to the distribution of PFAS in our environment. On the second hand, also we have the management of the waste. If this management has not been when we have the storage site or the waste of the incineration, all the products that can contain PFAS can also be diffused from these products to the environment. And if the management of the wastewater was not really sufficient, the PFAS can also still in the water and then come to the environment. So as I said, that the major source of the emission of the PFAS come really from the industry. We have different sectors that can be concerned in this emissions. We have all the industries that produce fluoropolymers, the textile, the cosmetics, the automotive, and also the electronics. How is the type of these emissions? These emissions can be either by air emission or soil water emission, or the soil contamination around the site, also by the water they emit, or by the run of water also that can arrive from the management wastes. So here is a bit of the PFAS contamination in Europe. In 2023, like a project called Forever Pollution have been conducted, and they have been found, and from this project they have produced this map, and it was first published by Le Monde before it's published also by a peer-reviewed article. And from this project, they found that more than 23, sorry, 23,000 sites have been said that all these sites contaminate are contaminated by the PFAS. And also they found that more than 21 sites are suspected to be contaminated also by PFAS because of the history of the use of this type of molecules. After this, there have been the CNRS have been started a new project called PDH, which is PFAS Data Hub, where you can scan here the QR code to see information about that. And the aim of this project, it was to have a technical and operation solution so that data keeps on being updating, so we can have a bigger map that is updated every couple of times, so that we can have more completed data. So I really invite you to scan this QR code and see also the map that's being updated every couple of times. So now we know about the PFAS, so it's also important to know their impact on human health. Actually, the literature and the bibliography part for the human health is also and for related to the PFAS and their potential on the health effect is really growing like continually. So PFAS have been found in the human blood, it's the human placenta, also in the kids. And for now, the main potential effects that are being that have sufficient level for evidence, we know that the effect is that they decrease the immune system responsive for the vaccination. We have also the effect like the dyslipidemia, the decrease of birth weight, and also increase the risk of kidney cancer. And in December, in December 1, 2023, also the International Agency for Research have classed the PFOA from as carcinogenic to humans, and they passed it from group 2B to group 1, and also PFOS, which is also another type of the family of PFAS, is also classified as possibly carcinogenic to humans, so group 2B. So now we can see how these PFAS can be really harmful for our health and also for the environment. It's really important that we know all these, but we really need solutions. So what are the current status for the regulation? So for now, internationally, it's started with the Stockholm Convention, which is an international agreement that regulates several compounds, PFAS and other also chemical compounds. In 2009, the production of and the use of PFAS has been restricted, and in 2020, the PFOA has been banned from importation, exportation, and from the production. But either even though this has been like banned because it's really hard to be braked, so it's still in the environment or in the water or some site. In 2022, the European Union decided to ban also the production of another product of the family of PFAS, which is the PFHXS. And they added this molecule to the persistent organic pollutant, the POP pollutants. In Europe, there have been like now many efforts for the actions to be done to supplement the Stockholm Convention to put more and more PFAS compound in this list, and the aim of the European Union in general for the regulation is to only allow PFAS to use only for the use that are considered truly essential to the society. So if we go for the definition of the essential use, we can see that they defined it as like it's essential for the PFAS is considered to be truly essential if two conditions was met. The first one is that it's essential for the health, the safety, and the proper function of the society, like the medical devices, protective equipments, and critical industrial applications. But at the same time, they also must be no alternative for these products to be used. So in case these two conditions was not met for the molecules, so the use of this PFAS is considered as non-essential, and then they are prohibited. So this is very good start for the humanity and for everyone on Earth. So let's see if gonna be really implemented. In France, if you want also to see on the national part, in France, it's started in 2023, where an action plan have been published by the minister to strengthen the protection of the population on the environment against the risk linked to the PFAS, and they have limited the concentration of the PFAS in the wastewater discharges to 25 microgram per liter. After that, in April 2023, also the report, another report have been also published, and to have like recommendation to strengthen also to monitor these PFAS. So after that, in June 2023, we had a decree that from the ministers, and the aim of this is to have a requirement on monitoring the waste charge, the concentration of PFAS in the waste charge of the industry. So all the industries in France must perform 1 to 3 analysis per month in their discharge, so they can monitor the concentration of the PFAS to see if they have PFAS in their waste or they don't have PFAS in their waste, and if there, so they can manage how they can reduce the risk of the distribution to the environment. So also completing with the regulation, so the European Union in 2020 have put also like concentration limit for 20 PFAS in the on the tap water, and the concentration must not the sum of 20 PFAS must not increase or pass the 0.1 microgram per liter. And for the raw water that are considered to be used for the human consumption also, it's the sum of these 20 PFAS must not also be more than 2 microgram per liter. In soil, which is what we are here for, there has been studies that have shown that the PFAS, notably that PFOA and PFOS, have been reported in the soil, and their concentration can go from 0.001 to 37 microgram per kilogram. So the interval is really big, but this depends on where the soil is collected from. So for now, there is no regulation currently due to its complexity and the lack of standardized protocol. But at the same time, there is ongoing actions to have more sustainable soil. It must, like in the European Union, they proposed to have a framework to ensure the soil health by 2050. And also, for example, the project of E-SPFdigit that work also on the soil sustainability by monitoring all these type of contaminant that Maxime have introduced in the previous presentation. So the question is why the regulation exists in water but not yet in soil. So as you know, that the water is the direct human source exposure. So we are all directly exposed to the water, especially the tap water. Also, the matrix of the water is really simple compared to the soil or sediments. And also the public is being really concerned by focusing on the drinking water. So for that, they have been developing many standard methods to extract these type of PFAS. And because we have really standardized methods, this allowed to have like a homogenized methods of extraction and analysis, which can allow to have good information, and then a good part of putting the regulations. So as I said, the matrix is really complicated, and we don't have really standardized methods. Every lab have his own method for now, and so for that we cannot compare. And so if we cannot compare, we cannot give really an accurate value for the regulations. So I will start now by the extraction techniques of PFAS from the case in soil and sediments. So all the PFAS extraction from soil are really based on the same principle, which is the solid liquid extraction, which is to add solvent extraction, an organic solvent to the soil, and let the PFAS pass from the soil to the liquid solvent we added. And in this step, in this method, we have really different steps that we need to process in it. So first, it's the extraction process, which contain also that shows we need to choose the solvent, the volume of the solvent. We have the shaking also. We have to choose the time and the speed of shaking between the soil and the solvent, the ultrasonic, the centrifugation, the filtration, the cartridges we use, and the number of extraction we have. So in each mini step, we have also different parameters that we need also to regulate. So we have more optimized extraction. So that's, we said, like every step requires really big optimization for better extraction, and that's why every lab has his own methods because it can differ either on the change of the solvent extraction, on the volume, and the time of the shaking, or on the ultrasonic centrifugation. Some use filtration, some don't use filtration, cartridges, and the number of the extraction. So that's why we have this variability. So if I can give you like a basic example for an extraction process. So when the sample is soil is collected from the field, we take an amount of soil, we add it with an amount of extraction solvent that can be, for example, methanol or any other solvent. Then we agitate it, we pass on sonication, we pass on centrifugation, and this is the type when we pass it on the cartridges, which we have the solid phase extraction, where we can concentrate the PFAS, and after that we can analyze it in the lab using our analytical, like the analytical technique we use in the lab, usually the classical one, the LC-MS. So I will focus on the part of the solid phase extraction to explain you exactly also how we do it after we have the mixture of soil and solvent extraction. So here you can see the real support, like this one is image as this one, this instrument. So we can see that we have this cartridge that has a stationary phase, and it's the most also used method for the PFAS in the environment material matrices. So the aim of this part of SPE, solid phase extraction, is to concentrate the analyte of interest and to eliminate interferences. As you know that the soil contain many different molecules or other than our molecule of interest. And how this works, actually, this stationary phase will have an affinity to the compound of interest, so it's gonna be absorbed on this part, and after that we're gonna add another solvent we call elution solvent, so that we can elute our molecules. So to give you a real example, it's so after we mixed the soil with the solvent, we agitate and we let the mixture to be in the pause a little bit. So we take the supernatant from here and we pass it on the cartridges, and this cartridge must be deconditioned before. So we add like 6 milliliter of methanol, after that 6 milliliter of water, so that the cartridge is ready to receive our sample. After that, we have the second step, which is the molecule fixation, which after we add the supernatant in our cartridge, the molecule of interest we're gonna absorb on the stationary phase with other interferent. After that, the second step is to eliminate the interferences, the interferent molecules, and the final step is to elute our molecule of interest by adding an elution solvent. Usually it's methanol 0.1 and NH4OH. And after that, the sample is ready to be analyzed. So where do we analyze this sample? Usually we analyze it in the liquid chromatography, mass spectrometry. There are many different methods to analyze the PFAS, but I will focalize on the LC-MS because it's the most used one, especially in the environmental matrices and the biological matrices. So what we have, so the sample we eluted from the cartridge, we're gonna pass it to the liquid chromatography. So here it's gonna pass on the called the LC column, the chromatographic column, where the molecules, different molecules, gonna be separated. After that, it's gonna be assimilated to the analyzer, to the mass spectrometry, where it's gonna be detected and so the identity of the molecule can be confirmed. This method, it's really sensitive. It can analyze between 40 and 100 molecules of PFAS, targeted PFAS. That's mean that we already know that then the type of these PFAS, we know the information regarding these PFAS. So we put all these information in the system of the LC-MS, and after that we can detect their presence in the samples or not. And also we have different development for the method we use in this liquid chromatography. Different agencies have been like Agilent or Thermo Fisher have been also working on the development of an accurate methods so we can to analyze these molecules. So I will enter with you in the details of the the detection analysis. So I will be in the case of the PFOA. I will take the case of PFOA because that's we are working now on it. So after we inject the sample in the LC-MS, it's gonna pass with the chromatographic column where the mixture is gonna be separated. So after that, we're gonna have one molecule, our molecule of interest that gonna be entering the mass spectrometry. So in what we see here, we have the molecule like the solvent which contain our molecule of interest. It's gonna enter the ion source. Here the PFOA is already negatively charged, so it's not gonna be ionized, but it's gonna be transforming from the PFOA in the solvent as a droplet to an PFOA in the gas phase. So the solvent is gonna be eliminated. We will only have our PFOA in the machine with some interferent molecules. After that, they're gonna be assimilated to the analyzer. And here we have MSMS. So we have three analyzers. The first one is the first quadrupole, which called Q1. It's gonna be the mass. We gonna define that the mass of this quadrupole is gonna be like the same mass of PFOA at the end at the first. So only the molecules that have this M over Z gonna enter the first quadrupole, and the one that don't have this mass gonna be ejected to the trash. After that, these molecules, so our PFOA, gonna continue its chemin to arrive to the collision reaction cell, where we have a gas, which is also recognized always as argon. Here, the PFAS, the molecules gonna be enter in collision with the argon, with the gas, and the PFOA gonna be fragmented into different products. We're gonna have three sub-products. The one of them is really the bigger one, so it's gonna be the main one, and the other one we're not gonna be really they have really small intensity, if I can say that, and they are not gonna be considered. So these all products will continue also their chemin to arrive to the second quadrupole, where we gonna also define the mass over Z, the mass for it. So this mass is defined as the mass of the main product we release after the collision. So only the product that have this mass gonna enter the quadrupole, and the other one gonna be ejected. And so after that, when they pass the analyzer, they are gonna be detected. After that, we're gonna have the chromatogram of that is the intensity of our product with the peak of our products as function of the time retention. So what we have at the end as result, what we obtain first a chromatogram, which is show our product at which time gonna exit the chromatographic column. After that, this peak is gonna be confirmed by the mass spectrometry in the chain I explained before, and we're gonna have the presence of the 369 m/z, which gonna confirm for us that this molecule is related to the PFA. So how we analyze in case we have an sample that we don't have any idea about its concentration of PFA? So first of all, we first do a calibration curve. So we prepare different solutions of PFA that contain a very determined concentrations. We do the plot of area as function, the area of the peak, so the blue one, as function of the concentration we prepared, and we we have the calibration curve, and after that we have the area of our sample that we don't have any idea about its concentration. We took the area of it, and we're gonna have by extrapolation the concentration of the PFA in our sample, or also we can use it using the equation of the curve. So the LTM-SMS is really a very good technique. It's really help with the detection of the PFA. It's really sensitive. We can go with a really small concentrations, but the inconvenient of the LCM-SMS is that it's really we need to pay for that. It cannot be used by anyone, so we need really a scientific person to use this method. And that's why we have a strong need for on-site analysis, and particularly in the environmental medias. So for now, to date, we don't have any simple tests that it's available to have a quick detection for the PFAS directly on site. And for now, also, it's not possible to have a continuous measurements and monitoring of the PFAS concentration over the time. So that's why the need is bigger and bigger, but at the same time, we have really progress on that. We have really some research that is really now worldwide underway to develop electrochemical sensors measurements that enable a rapid and low-cost detection. Example for what we are doing now in the E-SPFdigit project. And now I'm gonna leave you with my colleague Adil, that he's gonna explain for you more about the electrochemical sensors and more related to the PFAS detections. And I'm really happy to have your questions either now or after the session at the end, and don't hesitate to really explain to really ask your questions. So I'm gonna end the share now.
Anastasia has opened the conversation. Don't hesitate to write your question, please. Now, Adil will explain how to manage electrochemical analysis of PFAS. Adil. Thank you, Malak. Really, really nice. Really interesting. Yes, really. Adil.
Yes, just 1 second, and I will share my presentation.
Right. Waiting, Adil. In next March, April, we will prepare a training session on site. We will send you the details later. Adil.
So, hi everyone. Thank you, Malak, for your nice talk. So, my name is Adil AIT-YAZZA, and I will be presenting the third part, which is about electrochemical sensors for PFAS monitoring in the analysis. So this is the outline of the presentation. First, I will describe briefly how electrochemical sensor works. After that, I will present. After that, I will present 2 examples of electrochemical methods that are typically used in electroanalysis. And the third part is devoted to examples from the literature about electrochemical sensors that are used for detection of PFAS, particularly the PFOA. And finally, I will talk in detail about electrochemical sensor for detection of PFOA based on molecularly imprinted polymer. So how an electrochemical sensor works. The role of an electrochemical sensor is to convert a chemical reaction or an event into an electrical signal that can be measured. And typically, an electrochemical sensor is comprised of 3 major components. First, we have a recognition element that enters in contact with the sample that contains the analyte, and this induces an electrochemical change or chemical change. The second component is the transducer, and the role of this transducer is to convert or transfer the electrochemical change or the chemical change into an electrical signal. And typically we use for the transducer we use 3 electrode system like the one we see here at the left. It's a screen printed electrode that has 3 electrodes. An auxiliary electrode at the left. In its center, there is a working electrode. In this part of the electrode that is modified in order to make the sensor sensitive to the analyte or to the molecule that we want to analyze. In the third component is the signal processing element is the signal processing element and display unit. And this slide shows 2 examples of electrochemical methods. On the left, we have the potential profile of cyclic voltammetry. And the core principle of this method is to apply an increasing potential, a linear potential in respect to time, and the potential is applied forward and backward. And the response that we get is described in the voltammogram below. It's called the duck. It's similar to a duck and has two parts. The first part or the first peak, it corresponds to an oxidation reaction. In the backward path, it corresponds to the current that results on a reduction reaction. At the right, we have on the right we have the second method, which is called differential pulse voltammetry. And unlike cyclic voltammetry, in this method we apply like two potentials simultaneously. First, we have step potential. On top of this step potential, we apply potential pulses during very short periods. In the signal that we get from this method actually is a difference of current. It's the current that we record below is the difference between the current just before applying the pulse in the current that we measure while applying the pulse. In this voltammogram that we get below corresponds to the oxidation, to an oxidation reaction. So whenever we see a voltammogram, whenever we obtain a voltammogram that resembles to this after doing a differential pulse voltammetry, it's typically an oxidation reaction. Now moving to a few examples from the literature in which the many researchers have developed electrochemical sensors for detection of PFAS. In this work, the authors used the interaction of PFOA on graphene. In according to the authors, the PFOA undergoes an adsorption and partial degradation on the surface of graphene when we apply an increase in potential. In the figure that is at the right is different voltammograms that the author reported after increasing the concentration of PFOA from 0.3 micromolar to 3.5 micromolar. In the second work, the authors adopted a different approach. In this work, they coated the surface of the electrode with the perfluorinated anion exchange ionomer. It's not generally, it's just a membrane that have an affinity towards the anionic part of PFOA. And in this work, they coated a platinum electrode with this anion exchange membrane, and they monitored the hydrogen evolution reaction. And as the concentration of PFOA increases, the increase in concentration of PFOA induces a decrease in the activity or in the hydrogen evolution reaction. In the third example, it's an indirect method. It's based on creating a polymer or electropolymerizing an ionomer on the surface of a gold electrode in the presence of PFOA. And at the end, we get a polymer layer with cavities that are complementary to the PFOA molecule. in the way we measure the concentration of PFA in this case, and I will talk on this in detail in the next slide, is by using an electrochemical probe. First, we measure the response of the sensor to an electrochemical probe just after removing the template or the PFA from the cavities. For example, the black voltammogram corresponds to the response of the electrode when the cavities are free of PFA, when there is no PFA in the cavities that we created on the polymer. In the red, voltammogram corresponds to the response of the sensor to the electrochemical probe when PFA is occupying the cavities. So the difference between the peak currents of these voltammograms corresponds to is proportional to the concentration of PFA. And this is the measurement setup that we use here in our lab, and that was used also in the previous works. Typically, we have potentiostat that allows us to select different electrochemical methods and apply electrochemical methods by applying potentials. It applies potentials. Typically, it applies potentials in measures current, and we have also an electrochemical cell where or electrochemical connector where we can plug our electrode. We can either use this cell as we can either plunge or submerge this electrode in, for example, in 25 milliliter cell, or we can use directly small volumes. We can put the electrode horizontally and use very small volumes in the order of 60 or 70 microliters. And this slide shows gives an overview of the process that we use to prepare a molecularly imprinted polymer that is more or less sensitive to PFA. First, we start with the fresh electrode, and after that, we electropolymerize the monomer orthophenylene diamine in the presence of small concentration of PFA. In the third step, after the electropolymerization, we remove the templates or the PFA molecules from the cavities by putting this step is carried out in solution that contains typically ethanol in water, and after that, just after that, we can measure the response of the electrode to electrochemical probe. And this gives us this red, as I said before, this gives us our baseline that corresponds to the initial state of the electrode where no PFOAs or no PFOA molecules are occupying the cavities. And after that, we can, once we have our baseline, we can test our sample, and just afterward, test again the electrode in the presence of the electrochemical probe. And the difference of these two peaks will gives us the concentration of PFOA. And this is a more detailed steps of the measurement protocol. First, we start with measuring the we start by establishing the baseline of the sensor. Next, we rinse the sensor. We rinse the surface of the sensor, and we add our sample that contains PFA. And after 10 to 20 minutes incubation in this solution, we rinse the sensor again. Then we take a second measure in the presence of our electrochemical probe. At the end, we use our calibration curve that we established beforehand, and we determine the concentration of PFA in the sample. And this is just to give you a taste of how it looks, the electropolymerization of orthophenylene diamine, and how the MIP is created. This voltammogram at the left shows 25 cycles created by cyclic voltammetry on graphene electrodes. In the first, for example, the first voltammogram corresponds to the first layer of polyorthophenylene deposited on the surface of the electrode. And as the number of cycles increases, we see that the current decreases. And this is normal because the electrode becomes less and less conductive. At the right, we have another test that is typically conducted in conjunction with the molecularly imprinted polymers electrode. In this test, we do the same. We start from a solution that contains orthophenylene diamine, our monomer, but without the template, or without PFA. And we will see in the next slide a comparison between all of these, between three or four different electrodes. First, we have an electrode that on which we electropolymerized the orthophenyl diamine in the presence of PFA, before and after the removal of the template. And after that, we have also the response of an electrode on which we electrode deposited only orthophenylene diamine without the template or without the PFA. And finally, we have an electrode, fresh electrode or unmodified electrode. And we see that the highest peak corresponds to the unmodified electrodes, because the electrochemical probe has free access to the surface of the electrode. That's why the oxidation and the reduction signals are the highest, and the lowest signals come from the non-imprinted polymer, the electrode on which we electrode deposited only the orthophenylene diamine. This is just the same test, but it was conducted using differential pulse voltammetry. As before, we see that the highest signal corresponds to the unmodified electrodes, and after that it comes the electrode that was emptied from the template, or the electrode that with cavities without PFA. In the third position comes the electrode with the MIP with cavities full of PFA. And at the end, once we have established our calibration curve and extracted the PFA from soil, as Malak described earlier. We can use we can test the PFOA extract, the solution that contains PFOA and extracted from soil, and test it after establishing our baseline, and this gives us the concentration of PFOA in the sample. Thank you for your attention. If you have any questions.
Thank you. I think that we have the
Thank you,
question
Adil.
in. Yes.
I think we have a question in the Q&A part. So I'm gonna answer you here directly. So Gulit Defo, your question is that during the collection of sample, at what depth samples are taken? So regarding PFAS, actually PFAS depends on its chain. If it's the long chain, so the PFAS not gonna be enter really in depth in the soil. So usually we can go from between 0 and like from the surface to 10 centimeters on in soil for the case of the PFAS actually. And for the second part of the question regarding the ionization source, so it's either by SE electrospray ionization or APCE source. So usually we use more for the PFAS the ESI ion source because it's more like intense than APCE, but of course that the source of ionization can influence the intensity of the sample. But in the case of the PFAS, ESI is the most used and for the PFAS, especially if in the part of, for example, for the PFOA, so it's used ESI in the negative mode, for example.
Okay, Malak, a second question is focused on the maybe if you have information about the transfer of PFAS from water to plants, not from soil, but from water to plants. It's linked from soil, from water to plants. What can we respond today?
Actually, it depends really on the how do they treat water, like if you meant the plants, usually plant depends really on the plant itself, because I'm not really into the vegetable things, but I think that the cells have barriers, and we have the barriers and each barrier is like vary from a plant to another. So it depends on the plants. Some studies has shown that the PFOA can go only to the how to say it to the tige and the feuille. How to say it in English?
Please, yes.
I forgot the name. That
I can complete if you like,
yeah.
Malak. I can complete that because you have you remember the Malak fixed limit in wastewater or yes, from wastewater to the wheel to the environment, and the limit is 25 microgram per liter. The necessity will be to be under 25 microgram per liter in water for irrigation. That is the first step, but the next regulation will decrease a lot this value to 10 microgram per liter, and so on. And actually, all scientists work on this question. This is a big question for us to manage to better explain the nexus soil plants, and it's really difficult to give a frank response today. But we have some results, but it is on one-shot measurements we did on tomatoes. And the bibliography, Malak, well, you did.
And yes, the
yeah.
bibliography also has shown that the PFAS can also be transferred from water or also like from soil to the plants. But there is not really a comparison between different type of plants and different type of fruits or something like this. So it's really, I think that it's really depending on the type and the concentration also in the water or in the soil that it's already here. I hope I answered or we answered for your question, Bilach. I think also we have another question from Gulit for the SPE regarding also the electrode, if I may.
Adil,
I think.
question for you. How to prevent the degradation of screen printed electrode in the presence of PFAS, especially knowing that fluorine has a negative effect on the conventional working electrode?
Normally, screen printed electrodes are designed to be used just one time. So if for example, if an electrode, in our case, we can use the electrodes once they are calibrated. We can use them only one time. Not know if it's if I answer to your question.
I don't understand why fluorine has a negative effect on conventional working electrode. That is another question for me.
But
I don't know.
For just to add, because in the strategies that I presented, there is this problem, or the sensor is not exposed to fluorine, because the fluorine is attached to the carbon chain. It doesn't separate from the carbon chain. So the methods that I showed, they detect PFAS in indirect way. For example, in the molecularly imprinted polymer, there is no fluorine will not affect the sensor, because what we detect here is the PFY in indirect way. The PFY just occupies the cavities. In the signal that we get is the signal of the electrochemical probe. So I think there is no risk.
Yes. Adil, I can complete your talk, but the idea is not to do only one measurement, but the idea is to work on the regeneration step. That is the key to reuse the same sensor few times. So we are working on that, and actually we don't know. We lost a part of the signal after one analysis, but really it depends on the presence of natural organic matter on particles. So it could work, but we have to all people that develop screen printed electrode modified by MIP polymers are working on the optimization of the regeneration step with ethanol water mixture, or we have to improve that. Yes. We have another question, but
Yes.
for you, Malak, yes.
Yes.
Gulit again.
Yeah, sorry. In response for your question, actually, yes, the calibration curve will be changing from one ionization source to another. And even in the same ionization source, from our experience, we use the ESI and the negative mode, but at each analysis we do, actually we are obligated to do another calibration curve, because we cannot be like depending on one calibration curve that we had before and then test if it's gonna work or not, because even with our same parameters that are not changing, the calibration curves are depending on each time it's used. So from our recommendation, from our experience, at each time we do any analysis, it's better to have a calibration curve that it's done for that same batch of analysis. And of course, if in case of changing the ionization source, the calibration curve, the equation of the calibration curve will change. I hope that it gives you
Another question on the comparison of method, electrochemical method DPV and square wave voltammetry for Adil. Adil, do you have an idea?
Yes,
Why?
actually, we can use both methods, and here we used the differential pulse voltammetry because it's personal. Actually, it's personal choice because in our case, what we detect is the electrochemical probe. And the concentration at which we detect this electrochemical probe is at 1 millimolar. So it's high concentration. We don't need extremely sensitive method like square wave voltammetry. So at the end, we can use both of them as long as they can detect the electrochemical probe and give a clean signal.
Colin Perdrier, on the same way, maybe I miss a detail, but why slide 12 and 13 of Adil? The aim is to obtain the smallest peak from the target molecular oxidation, or not? I would imagine the opposite. So your aim initially was to obtain a smaller oxidation peak or higher? Well, what do you understand?
From
Adil, yeah.
I can return to the slide to explain it better. Okay, so the first thing, once our MIP electrode is prepared, like in step 3, we measure the response of the electrode to the electrochemical probe, and this will give us our baseline. With this signal, we measure the peak of this signal. This will give us our baseline. In the second step is to expose the electrode to the sample that contains the PFA. What will happen is that the PFA will occupy some of the cavities on the surface of the electrodes, and our electrochemical probe will not have enough cavities to have access to the surface of the electrode. So what we expect is that the signal that we will get after exposing the sample after exposing the electrode to the sample, we expect to have a small signal because the available cavities are the number of available cavities is smaller compared to the pristine, let's say, surface of the electrode. So that's why that's why the signal that we get after the incubation or after exposing the electrode to the sample is lower. And this is normal. This is what we want. We want the signal of the electrochemical probe after exposing it to the sample to be lower than our initial or our baseline. In this difference between the peak that we measure, difference between the peak before the incubation and after the incubation is proportional to the molecules of PFA that occupied the cavities. I hope I explained this part.